today the lectures on the server?
They're already, these, you mean these are videos?
The lecture, the Tuesday lecture and today. You can put it in the server video?
They're, the notes are already there. Oh, well, depends on how much.
But he said this, the last things it's lecture 16.
Okay, so he's going to the server and not seeing it, right? So I'll put it on the server.
Oh, thank you.
Okay, what comes next is our problem-solving session. Let's go, today, I'm just gonna go over a bunch of problems. You know, make sure you understand what I'm doing and ask questions, because the problems like this will be on the finals. So, very much maybe some exact problems are gonna be, because I just copy sometimes from the notes. All right, so let's look at the first one. I have a filter. So linear system has frequency response with a magnitude h of f given as cosine pi f over 1000 for 0 f 250 hertz, 500 hertz, and 0 otherwise. So that's the frequency response of my filter. At the input of the filter, there is a thermal noise with the room temperature. So at the input, there is a thermal noise with a temperature T equal to 300 kelvins. That's a room temperature. Room temperature is 300 kelvins. It's a little bit warmer room, right? But it's a round number, so that's why I remember. So it says here, calculate the power spectral density of the noise. Calculate power spectral density of the noise. What's the power spectral density of the noise? And 0 is equal to kT, right? Where K is the Boltzmann's constant, T is the temperature expressed in kelvins. So this is 1.38 times 10 to the minus 23 joules per Kelvin times the temperature is 300 Kelvin, and this ends up being 414 times 10 to the minus 21 watt per hertz, or sometimes we use in the problem 4.14 times 10 to the minus 18 milliwatts per hertz. Usually we just round it. We say 4 times 10 to the minus 21, 4 times 10 to the minus 18. So those are the numbers that you should kind of remember. The part B, calculate the power of the noise at the output of the system. Now, how do I do that? Well, I know that the power spectral density at the output is going to be magnitude of F squared times the power spectral density of the noise at the input. This is the relationship that comes over and over again, right? Tells us how the random processes propagate through linear time invariant filters, and this is the equation that explains that. In our case, the input is the same. It's KT for one sided and KT over 2 for double sided. So let me explain this a little bit, because it comes all the time, right? Make sure that we understand. If we talk about one-sided power spectral density, which is, what do you call this, N of F. This is this, KT, right? In physical, in the physical world, frequencies are always positive. So this is what exists out there. You know, when we talk about power spectral density of the noise is defined only for positive frequency. Mathematical model for that comes handy in all of our examples and all of our studies is something called double-sided. And double-sided power spectral density of the noise is KT over 2. But now it exists for positive and negative frequencies. Now, what does this mean, right? Have you ever thought about it? I'm sure you did. Do you know how to explain yourself that? This is looking, remember the noise is consists of all of these little sinusoids. Every sinusoidal cosine of 2 pi f is equal to that 1/2 e to the 2 pi f plus ft, plus e to the minus j 2 pi ft. So there are these two exponentials, one going at plus f and the other one going at minus f. So these are the guys that we're plotting when we're plotting double-sided. We're not plotting the whole cosine, but we're plotting these two exponentials. And they're here. One of them is here, and the other one is over there. So every noise component in a one-sided representation can be decomposed as two exponential components at the double-sided representation at the half the magnitude. The way how you get this one, you take this axis, flip it over, and then you add it to, right? And then that's what becomes the other side. So when you integrate one-sided, then you integrate only over positive frequencies to get the power. When you integrate double-sided, you have to integrate over negative and positive. But usually we still integrate over positive. It's just we amplify by 2, multiply by 2. So in our case here, we asked to determine the power. Sn of f is double-sided. So here, I'm going to say power, and the output is going to be integral from minus infinity. F goes from minus infinity to plus infinity. H of f, magnitude squared, times s input of f df. This is equal to integral when f goes from minus 500 to plus 500 cosine squared of 2 pi f over 1000. So that's your magnitude squared. Outside of this interval, h of f is equal to 0. Therefore, it's not, we don't integrate outside of this interval. And then, what should I write here for the power spectral density of the 1 over 2 times kT? And then df. Why 1 over 2? Because this is a double-sided in this expression, right? And you can see I'm integrating over the entire x. So now this integral can be easily solved. Let me just see what happens. Go ahead.
What we use here at the first k of t, don't 1 over 2 k of t at the first power spectrum.
Why do I put here n0 is just, I guess, why did I use it? Because I always quote this number, right?
No. Why you don't divide it by 2? Because it is one-sided.
Yeah, one-sided. This one-sided. When I say, in a lot of times, I say, what's the power spectral density of noise? 4 times 10 to the minus 18 milliwatts per hertz. And a lot of times I don't say anything else, right? So the question from you should be, well, is it double-sided or one-sided? That number that I quote, 4 times 10 to the minus 18 milliwatts per hertz, is one-sided, right? And that's where it's coming from, right? I mean, I could have said let me just actually say it. If I were to say S and I of F, I would put 1/2 times 4 times 1/4 times 10 to the minus 18 milliwatts per hertz. So this is double-sided, this is single-sided. It's just a factor of 1/2. Always just be aware of which one you're working with, right? Now, let's do this integral. Here, I'm going to multiply by 2, integrate from 0 to 500, and this 1/2 will cancel. So this becomes kt, integral from 0 to 500. And then I have cosine squared pi f over 1000 df. And I'm going to introduce now substitution. X is equal to f over 1000. Therefore, df is equal to 1000 dx, right? And my power and the output becomes df is 1000 dx, so 1000 goes outside. So it becomes 1000 times kt integral. When f is at 0, where is x? At 0. When f is at 500, where is x? At 1/2, right? So it's 1/2 of the cosine. Now, f over 1000 is x, so it's cosine pi x squared dx.
Excuse me.
Uh-huh.
The question is cosine pi f or 2f? 2 pi f?
I think pi f. Pi f.
When you,
Hmm?
when you get the square, it's going to be cosine square 2 pi f over 1000.
Why?
Pi f there and then pi f in the back.
Oh,
This is
no, no,
the-
pi f. Pi f. Now, what's the value of this integral? That's the question. How would you evaluate that? Yeah, it's easy. You just decompose it as 1/2 plus cosine 2a. You can do a trick. You have to be a little bit careful, but you can do. Remember that trick that I always do when I say, well, cosine squared plus sine squared is equal to 1. And then I can integrate, and half of it goes to cosine, half of it goes to sine. So if I were to integrate 0 to 1/2 of 1 dx, what do I get? Half and half of half is 1/4. So this is 1/4. So this is 250 kt, or 4 times 10 to the minus 8. What do I have here? So this is 250 times 4 times 0.14 times 10 to the minus 18 milliwatts. And this is hertz divided by hertz here. So this ends up being 1.03 times 10 to the minus. This doesn't seem right. Minus. This is not right. 250, let's say 250 times 4, it's 1 point, so 50. Okay, so the intermediate is not correct, but this one is correct, so it's 91.9.8. So that's the output power of this. And then the part 3, I want you to be really, really alert. This is, I remember, I took this problem from one of the comprehensive exams. Comprehensive exam is what we give for master students, where they are to graduate. And the third part was given like this. If the signal S of t equal to 4 sine squared 2 pi times 1000 t is presented to the system, find the is presented to the input. What is the output? I tend to, when I gave this part, I thought, okay, let me give some free points, right? This is very easy to solve. And to my surprise, very few students came up with the correct result. How would you even tackle this? If you have this signal S of t presented to your, what is the power of the You have h of f. You have here S of t, and I'm asking you to determine power of this signal, the output. How would you tackle this problem? What would you do? Go ahead.
Find the power spectrum
Uh-huh.
and multiply by,
Power spectral density of this.
yes.
Okay. That's what a lot of them did, right? And that doesn't give you, I mean, you can do it in general, but that's not how we think when it comes to these problems. When you have pure sinusoids presented to the linear system, you do time domain, right? Let me just give you a first step here. Let's say S of t is equal to a cosine 2 pi f0 t plus some phi, right? I present this sinusoidal to this h of f. What comes at the output? Y of t is going to be magnitude times the magnitude response h of f equal to f0. So this is how the system acts upon the sinusoid. It modifies the magnitude by the magnitude response and adds to the phase response. So then I write cosine 2 pi f0 t plus phi plus the angle of h of f equals 0. So that's how we calculate, right? We don't actually even calculate, we just write it out. Right? We know this. Now, what is the power of y of t? Is a squared over 2 h of f equals f0 magnitude squared, right? So that's the power of the output. You agree? Magnitude squared, and the magnitude of this one is magnitude of the input times the magnitude response of the circuit. Now, in our case here, sine S of t is not pure sinusoidal. It's 4 sine squared of 2 pi times 1000 t, which is 4 times 1/2 minus 1/2 cosine 2 pi times 2000 t. Okay? So you have two components. Let me just take one step further. One is the DC component, 2 minus 2 cosine 2 pi times 2000 t. So this filter is now going to affect both of these components. What is the response of the filter at f equals 0? Look at it over there. Magnitude response of this filter when f is equal to 0. Is what? Cosine of 0. Cosine of 0. 1, right? So what comes at the output, y of t, is equal to 2 from this guy. What's the response at the frequency f equal to 2000? If f is equal to 2000, what is the response? 0. Right? That's the output. What's the power of the output? So that's how you would do this, right? In general, watch for this relationship. This is like my biggest amazement when I look at your exams and tests and everything, right? This appears all the time. And very seldom students get it right. Now I know you've seen this, you have, right? Many, many times. But I'm still puzzled, why does it take effort to remember, right? It's a central piece in everything we do. So make sure this is just as important as the one that I had before that tells us how the power spectral density changes. It changes, it goes, all the random process changes, it goes to a linear time invariant. So make sure you know this. Okay? All right, so that's first part. Let's look at the next one. Oh, sorry. All right. So the next one, it says consider transmission using double sideband large carrier. So this is double sideband large carrier. Assume the following parameters. W is equal to 4 kilohertz. The modulation index is 0.4. Normalized power of the modulated signal is equal to 0.5, so we're actually modulating this with a pure cosine. Required signal to noise at the output is 35 dB, and KT is given 4 times 10 to the minus 18 milliwatts per hertz. Is this single-sided or double-sided? Single-sided. Thank you. F is equal to 10 dB. This is noise figure. Now, it says calculate the power of the noise at input. Okay, forget about this. Because I don't think I did this for another problem, but I don't think I use it in the problem. So let's stick to this. So that's the power of noise. So what is the power of the noise at E? First, we know that the power of the noise is going to be bandwidth that is utilized times the power spectral density of the noise, right? If I'm working single-sided, what's the bandwidth that I should put here? What is the bandwidth of double sideband large K? 2W, right? So it's going to be 2W times KT. Let's say I worked double side, then I have 2W for positive and 2W for negative, right? So this would be for single side. For double-sided, I get 2 times 2W, but my power spectral density is KT over 2, right? So you get the same result, right? So as it should be, you always get the same result. But just always be cognizant, right? Double-sided. Right? It's a frequent place to make mistakes. There's nothing complicated. It's just that you have to be, you can't be sloppy. You have to kind of think along the way. So that's the formula. And here I have 2 times my bandwidth is 4 kilohertz. And then times the power spectral density, KT is 4 times 10 to the minus 18 milliwatts per hertz. So let's see here, I have 4 times 4, 16 times 2 is 32. So it's 3.2 times 10 to the minus. I have 18 and 3 minus 15 and 1 minus 14 million. And if you take 10 log of that, this is minus 135 dB10 decibels relative to a minute. So that's the power of the noise. Power B, what should be the signal power at the, what is the minimum? Signal power. Anybody here from PCS or RF propagation? Yeah. How do we call this minimum signal power at the input to receive? No?
The minimum signal
Minimum signal power at the
Sensitive.
receiver sensitivity, right? Minimum signal power that you need to deliver to the receiver to meet its quality requirements is the receiver sensitivity, right? So if the receiver sensitivity is high, is it a sensitive receiver? If it's like -50? You want to say, if this number is if this power is high, is it a sensitive receiver? No, right? The receiver sensitivity, the lower this value is, more sensitive your receiver is, right? The smaller the power it requires, more sensitive it is, right? So how do I calculate that? Well, signal minimum is going to be your noise plus the signal to noise ratio at the input, right? Because I know that signal to noise ratio at input is the minimum that I need to have in terms of the signal to noise ratio at input. That plus noise gives me the signal, right? Of course, everything is here and everything is in dB. In or dBm. So, S minimum in dBm is going to be noise power, which is minus 135 dBm. Now, what is the signal to noise at the input? I have my signal to noise at the output 35 dB, but in a double sideband large carrier, these two are related somehow, right? What's the signal to noise? Let me just first calculate that one instead of writing this. What should be the signal to noise ratio at the input first? I know that the signal to noise ratio at the output is equal to 2 times A times power of the message normalized, 1 plus A squared power of the message normalized times signal to noise at the input. Just like all the other things, we have the signal to noise output is the processing gain times the signal to noise input, right? So from here, I can calculate the processing gain. This is all processing gain. And processing gain in this case becomes 2 times 0.4 times power of the message normalized is 0.5 divided by 1 plus 0.4 squared times 0.5. And anybody with a calculator? Can you calculate this? So it's 1, so it's 0.4
Times
divided by 1 plus 16.08, right?
it's 0.48.
This is 0.48? No, it cannot be. Because this is larger than 1. So it's 0.4 divided by 1.0.
0.37.
0.37. And then take the 10 log of that.
Minus 0.43.
times 10.
times 10,
So it's minus
4.3.
3 dB. So the processing gain in this case is minus 4.3 dB. Right? This is a double sideband large carrier. You remember the double sideband large carrier has a negative processing gain. Why? Because the signal power at the input includes the carrier power, which is really large. Signal power at the output doesn't. We eliminate the carrier, so your processing gain is always going to be small. So here, the signal to noise ratio at the input needs to be 4.3 dB better than the signal to noise ratio at the output. So this is 35 dB plus 4.3 dB. And this is 38.3 dB. So that's what I need to deliver to the input so that I meet my performance requirement at the output. Now, if I plug this in here, you get that your receiver sensitivity is going to be minus 135 dBm plus 38.3 dB, and that's 135, 100, minus 100 plus 3.3, so it's minus 96.7. So that's the minimum power that you need to deliver to this receiver to operate. And then the last question is, if the path loss between transmitter and receiver is 100 dB, what should be the transmit power? If path loss is 100 dB, what is the transmit power? Here's what, remember our link budget calculations. This is your S min. This loss here is your path loss. And then this is your transmit power, right? So you get that the transmit power, this needs to be your S min plus path loss, which in our case is minus -6.7 dBm plus 100 dB that you need to overcome. So you need to transmit at 3.3 dBm. 2.3, slightly over 2 watts, 2 milliwatts. Any questions?
Signal to noise at the input is 39.
Did I? 39. Oh, everything is dB, right? So 39.3, 95.7, 95.7, 4. Thank you. Okay. There's a mistake here in the notes. I'll have to correct it because I forgot that it's a double sideband large carrier. I did the problem as suppressed carrier. All right, let me do a couple more problems. Problem number 3. A double sideband signal with additive noise is demodulated by a synchronous detector with a phase error of 5. So here's the situation I have. I have my front-end filter, and here I have U double sideband suppressed carrier of T, and then I have my narrowband noise that is coming into the receiver, and I've demodulated this coherently, but with 2 cosine of 2 pi F0t, but my local oscillator has some phase error of 5. This is after pass through a low-pass filter to get my output signal. What is the, how large is the bandwidth of this one? 2W, right? Because it's a double sideband suppressed carrier. How large is the bandwidth of this one? Just the W, because I'm already at the baseband filtering my signal. So the question here is express signal to noise ratio at the output as a function of power of the message normalized divided by N0, power of the signal divided by N0 double, sorry, power of the noise of the baseband, right? Or just power of the message signal divided by this. All right, so how do we do that? Well, let's. This is just one of those problems. You work out through the chain here, and you calculate your signal-to-noise ratio, and hopefully we'll be able to express it as something that functions with these terms. So U double sideband suppressed carrier of T is going to be some carrier M of T times cosine 2 pi FCT plus phi. Okay. What about this narrow band noise? N of T, we know that it can be expressed as NC of T cosine 2 pi FCT minus NS of T times sine 2 pi FCT, where this NC and NS are baseband processes that have the same power as this process N of T. Now, when I multiply with the cosine here, let me call this Z here Z of T. Z of T is going to be AC M of T cosine 2 pi FCT plus phi plus NC of T cosine of 2 pi FCT minus NS of T times sine of 2 pi FCT. That's this whole stuff here. And then times cosine 2 pi FCT plus phi. Right? And you've already done this many times. So let's see if we can shorten this and kind of write out the results a little bit faster. Let's do it like this. AC M of T plus NC of T. That's the first two terms, times cosine 2 pi FCT plus phi. Sorry, there's no phi here. Just 2 pi FCT. No, not even phi here, right? FCT. And then times cosine 2 pi FCT plus phi. And then the second term is going to be minus and S of T times sine 2 pi FCT times cosine 2 pi FCT plus phi. Okay. Now let's just see if we can get y of t. Y of t cosine alpha cosine beta is cosine of the sum, cosine of the difference. Cosine of the sum is at twice the frequency of the carrier. Therefore, it's going to be eliminated with this low-pass filter. So the only thing that survives here is cosine phi. So I have here AC M of t times cosine phi plus NC of t times cosine phi. All right? So that's from the first one. Sine of alpha times sine beta is 1/2 sine of the sum and then sine of the difference plus sine of the difference. Sine of the sum is going to be at a double frequency, therefore it's going to be eliminated by the filter. So I have just the sine of the difference. So I have minus NS of t times sine phi. This is signal. and this part here is noise. Now, some of you might wonder, where did 1/2 go? 1/2 go because is gone because of these two here, which I forgot to put here. So I apologize. So there's two. Okay, so this is signal, this is noise. Let's take a look at what is the power of the signal. So power of a signal becomes AC squared, power of modulated signal, times cosine squared phi. Right, so this is average over time of this term squared. Power of the noise is going to be NC of t times cosine phi minus NS of t times sine phi, and I have to square that and average it over time. So this is NC squared average over time times cosine squared of phi plus NS squared over t average over time times sine squared phi, and minus 2 times NC of t times NS of t average over time times sine phi times cosine phi. Right? Any? Okay. So what is the average of this? Just whatever is the power of this guy. Right? So I can say that this is n squared of t. Right? Why? Because this noise and c squared of t has the same power as this one, right? Now cosine squared phi. What's the power of this one? The same as the power of the noise n squared. So I'm just going to write it n squared of t average over time times sine squared phi. What is this average of that? 0. These two processes are uncorrelated. So if you multiply them and average them over time, it's 0. So this thing is 0. Now, this is n squared of t. Cosine squared plus sine squared, 1. If I calculate this power in the frequency domain, what is it? What is the power of this signal n of t? 2w times n0. Excellent. So it's 2w times n0. So now if I look at the signal to noise ratio in the output, it becomes power of the signal, which is AC squared times power of the message times cosine squared phi divided by 2w n0. So I can write this as AC squared times cosine squared phi divided by 2 times Pm over W. Right? That's the result.
Why we use 2W?
Because the bandwidth, this is a double sideband.
But you give me output.
Yeah,
Output,
okay. We gotta be very careful. The power of the power spectral density of the noise at the output is not n0, right? The power spectral density of the output is 2n0. Noise at the output is 2n0. Remember, okay, this goes back to I made a remark in one of the lectures, and I asked you, can you think about it what is causing the processing gain in the double sideband suppressed carrier to be 2? Remember, we cannot derive it, but what does it mean? Why is it 2? Have you thought about it? Here's what is happening. Let's just take a look at what you have a double sideband. This is your carrier frequency. Let's take a look at 2 sinusoidal components. When I demodulate and I multiply with the carrier, where do these 2 components travel? I'm just doing one-sided, right? I'm just looking positive frequency. So this is now at the basement. So this is plus F, let's say F1, and this is minus F1. Where does this component travel? It gets mapped here, right? At F1, right? It's the difference, right? So cosine of Fc plus F1t, 2 pi Fc plus F1t times cosine 2 pi Fc will bring this component here, right? How about this one? No, same place, right? Both of these, here's what I'm talking, cosine 2 pi Fc plus F1t times cosine 2 pi Fct, right? So you have a sine, sum and a difference. Sum gets filtered out. Difference is cosine phi 1t, 2 pi phi 1t, right? The second component gets me the same, right? So these 2 guys add, right? So the magnitude here, magnitude is multiplied by twice. Power goes up by 4, right? If this is the magnitude of 1, this is magnitude of 1, this is magnitude of 2, therefore the power is 4. Okay? Now, let's take a look at noise. Now you have Fc, there's a little noise component, let me call it N1, and little noise component N2. Now, key thing here is these 2, origin of these 2 guys is the modulation. So these 2s are in phase. Whatever is the phase of this one, it's the same phase of this one. So when you bring them down, they will add in amplitude. These 2 guys have a random phase relative to each other. So although both of them will map to the same position, right? This one will go here, and this one will go here. They will add in power. Why do they add in power? Because they're not coherent, right? They're going to have a random phase relative to each other. So they're independent, so their power is sum of their individual powers. So here the power goes by 4 because you add in magnitude. Here the power goes by 2. Is multiplied by 2. Therefore, the power of the signal over power of the noise goes by a factor of 2. That's the source of your processing, right? You followed, right? Now, what happens if your carrier has now a random phase? It's not synchronized with the incoming carrier. Then you have this cosine term here on your signal, right? And in extreme cases, phi is equal to pi over 2. Nothing comes out, right? But when it comes to noise, since the noise has a random phase to begin with, you will always have the same power of noise in the output, right? To go back to your question, the power spectral density here is twice the power spectral density that you had at the passband, because you bring this down, you fold it over, it stacks as power, right? So that's the we'll do one more problem and then I'll give you some credit, because a lot of times I keep you over the time. It says, consider an FM signal with following parameters. This is problem 6. Or rather
Four.
5. I skipped one.
Ah.
Because it was easy, let's just do number 5. FM signal with following parameters. M of t is cosine 2 pi FM t, where FM is equal to 2 kilohertz. That's our modulated signal. Beta is equal to 5, and 0 is equal to 4 times 10 to the minus 17 milliwatts per hertz, so it's slightly higher. And signal to noise ratio at the output is equal to 45 dB. Okay. So first question, determine the FM threshold. For the signal. So what is the threshold? The threshold is the minimum signal level that needs to be provided as input for the processing gain to kick in, right? For the system to operate properly. Signal to noise threshold is given as 13 plus 10 log, or rather, where is it? 10 log, sorry, 1 plus beta. In our case, this is 13 plus 10 log of 1 plus 5. And when you compute this, this is 20.78 dB. So that's the minimum minimum signal to noise ratio at the input. Part B is very interesting. It says estimate signal to noise ratio and the input required to meet signal to noise ratio at the output of 45 dB. Okay? So what should be the minimum signal to noise ratio at the input so that the output is given 45 dB? First thing we do, we calculate processing gain in dB. And this is 10 log of 1 plus beta times beta squared times 2 times of the power of the message normalized. In our case, this is 10 log 1 plus 5 times 5 squared plus times 2 times 1/2, right? Because our message signal is the pure sinusoidal already normalized with power of 1/2. When you calculate this, it is 26.5 dB. Okay? So, now we say, okay, signal to noise ratio at the input is going to be 45 dB minus 26.5 dB, which is 18.5 dB. Is that a good answer? Why not?
The out is 45.
Out is 45,
Yeah.
processing gain is 26, right? So output minus processing gain gives me the input.
Right.
Is it correct? Yeah? That's the biggest mistake, the most common mistake. This equation here for processing gain is only true if the result that you obtain here is larger than a threshold, right? Right? So now you look at this and you can say, okay, it cannot be this low. The lowest that the signal to noise ratio can be and this system works properly is this. So this system cannot give you 45 dB. It will either be better than 45 or it's not going to work properly, right? So here, if this is smaller than S and threshold, therefore, signal to noise ratio of the input is gonna be equal to the threshold, 20.78 dB. Right? So very important, right? This is and it says if the path loss is 100 dB, estimate required transmit power. So C path loss is 100 dB. Well, the transmit power is going to be your signal plus over noise plus the path loss. Right? Noise plus signal over noise gives you the signal plus the path loss. Now, how large is the power of the noise? Noise is going to be 10 log of power spectral density of the noise per hertz times the bandwidth. What is the bandwidth here?
2 big.
So it's 1 plus 5 times 2 kilohertz, right? Times 10 to the 3 hertz. And this gives you the power of the noise, which is minus 120, 18 dBm. And now I have everything. I can say that the transmit power is going to be minus 120.18 dBm, plus the signal to noise ratio, which now needs to be at least 20.78 dB. And then path loss of 100 dB. And this gives me minus 99.18. No. It gives me, everything said and done, 0.82 dB. 1 dB. Little over a milliwatt. Okay? Any questions? Okay, that's it for today. There are a few other problems in the notes. As of next time, we're going digital. We're done with that.